Okay, so let's look at the group Z4. So Z4 is the group of, it's basically 1, 2, 3, 4. This set under addition mod 4, right? So another way of saying it is that we have 4 equivalence classes, which are like, say.
Sir, shouldn't it be 0, 1, 2, 3?
Yeah, you're right. Sorry. Thank you. Yeah. So there is a sorry, yeah, you're exactly right. Yeah, right. So we know this kind of, I'm not gonna write this out, but but there is another group which is called, say, Z divided by 5Z into, this is called the multiplicative group mod 5. So what are the elements of this group? So this group has 4 equivalence classes, but they all differ by 5. So -4, 1, 6, 11, 16, ... That's 1. 2 is, say, ... -3, 2, 7, 12, 17. And number 3 is ... -2, 3, 8, 13, 18. 4 is -1, 4, 9, 14, 19, ... Okay. So what is the multiplication? Is just group multiplication. It's just the usual multiplication. So if I take 2 and 3, then what I have to do is that I have to just take some representative, say you can take 12 from 2. And for 3, let's just take 3. So 12 times 3 is 36, right? So 36.
So which group has 0?
So this group doesn't have 0. Okay. So we have 1 because you can't really get from, yeah, so these are the equivalence classes that we are defining. Okay. So you see that 0 is not going to be an element here. But the idea is that, when we when we multiplied 36, if I look at where 36 is going to be, well, we have to divide it by 5, and whatever is left over is going to be its equivalence class. So 36 is going to be part of 1 bar, right? So we have 2.3 is equal to 1. So we have basically cleverly, found a subset of the integers such that under this multiplication modulo 5, that it forms a closed set and it has a group structure. Okay.
Yes, I got it.
So let's take a break and meet back here at 6:15, and then we'll show how the seemingly very different groups are actually isomorphic. Okay.
Sir,
That's 5, right? Divided by not 3.
Yeah, thank you for, it's a very bad handwriting. Yeah, thank you.
So Z4 should be 0, 1, 2, 3, right? Or 0, 2, 3, 4.
Again, you're right. Thank you. I don't know why I made all those mistakes. Okay. Yeah, thank you. Anything else? Any other comments? Typos? Errors? Okay, let's take a break then, and then we'll meet back here again. Okay, so I'm back. Shall we start?
Yes.
Okay, so just one comment is that, this new group, the multiplicative group mod 4, the way that we have, it's the equivalence classes have been chosen is that they exclude all multiples of 5. Right, so there's no 0, there's no 5, there's no 10, so that whatever we have left, the module, so none of the representatives are divisible by 5. So what we have here is that as the leftover, when we divide it, we have basically either 1, 2, 3, and 4, right? So that's how these equivalence classes have been made up. And on the other hand, if I go back to this thing, like all the integers are included in Z4, and it just it has a topology where 0 is identified by 4, and so on and so forth, right? So okay, so I'm kind of taking a little bit of a time, but I think it's worth doing. Let me give you the multiplication table. Let's write the multiplication table for Z4. So let's call this, so the multiplication for Z4 is essentially addition modulo 4. And we have 0, 1, 2, 3. And we can give them bars, 0, 1, 2, 3. And if you do the addition, we have 0, 1, 2, 3, because 0 is the identity element there, right? And then we have 1, 2, 3, 0, 2, 2, 3, 0, 1, and then we have 3, 0, 1, 2. Okay, so we could have, we can say write in a more abstract way, where this is a group multiplication, and the group elements, let me give us names E for identity A, B, C, E, A, B, C. Now, if I identify E to 0, A to 1, B to 2, and sorry, why am I giving bars? I don't need bars on the side. B to 2 and C to 3 bar. Then we have essentially E, A, B, C, E, A, B, C. And here we have B, C, E, B, C, E, A, C, E, A, B. So each row is essentially a cyclic permutation of the one before. And of course, like incidentally, you can observe that none of the rows are repeated, right? The ordering of every row is different. So this is the multiplication for Z4. Now let's, make the multiplication table for the other group. So the multiplication table for Z by 5Z. Okay. So if I do this, then what do we have? Here, let's just put into, and here we have, I'm sorry, 1, 2, 3, 4, 1, 2, 3, 4. Here, 1 is the identity element, so we have 1, 2, 3, 4, and immediately we can write 1, 2, 3, 4. But now you see that, if 2 times 2 is 4, right? 2 times 2 is 4, so okay, so we can put 4 there. 3 times 2 is 6. So which is yeah, 3 times 2 is okay, I think I made a mistake here. 1, 2, 3, 4. 1, 2, 3, 4. 1. Okay, so we have 2, 4. 3 times 2 is 6, so that should be 1 here, right? Then 4 times 2 is 8, so there should be 3 here, right? Is this correct? And then 3 times 2 is 6, so there should be 1 here. 3 times 3 is 9, so that's going to be 4 here. 3 times 4 is 12, so that's going to be 2, right? And then 2 times 4 is 8, so that's going to be 3. 3 times 4 is 12, so that's going to be 2. And here it's 1, right? Did I make a mistake? Okay, so now what we can do is that we can say, okay, if I have, say, if I have a abstract multiplication table now, then I have to identify, so, and if I identify E to be 1 and A to be 2, and say B to be did I make a mistake?
It seems like it's shuffled a little bit, like you have to rearrange the rows in order for them to match up.
Yeah, exactly. Yeah. So I think B is going to be 4 and C is going to be 3, right? So then the first row is going to be E, A, C, and this is going to be B, right? And
shouldn't it be EABC?
EABC, right? Yeah, exactly. Otherwise, it doesn't make sense here. So it has to be EABC, right? So then B has to be 3, right? I think I made a mistake. Let me just see. Oh, yeah. Yeah, I think I made a mistake somewhere. Just 1 second. Let me just look at my notes, okay? Just give me 1 second. I think I made a transcription error which has propagated. So let me just look at the notes. Just 1 second. So, right. Yeah, okay, so everything is good. So let me just I didn't make a mistake here, but let me just first rewrite this multiplication table, okay? So, we can always shuffle rows and columns, right? So not like shuffle rows. So we can write this as, say, so we have 1, 2, 4, 3. So what I'm doing is that I'm just exchanging this row with this column. And I will also do this, exchange this, these 2 columns and these 2 rows, okay? Then I have, and I'm just not gonna bother with the bars. Okay, so if I do this, then I have 1, of course, this doesn't change, this doesn't change. Here, 4 comes here, and then 3 goes there, and here, of course, what was before 2, 4, they won't change, but these 2 guys will now switch places. So we get 3 and 1. And now here, 3 and 4 will switch places. So we get 4 here, and we get 3 here. And we would get 2, 1, but except now, because we have also exchanged these things, we get 1 and 2. And now, and the last row, we get 3, 1, 2, 4. Yeah, okay, so this multiplication, these are the same multiplication table, right? Tables. And now suppose I say, let me call E 1 and then A 2, and then so A, we have their bars here, and B say 4 and C 3. Okay, and then what we can do is that we can then write this multiplication table in a more abstract form. Okay, so we can say this is E, and then A, B, C, A, yeah, E, A, B, C, and then E. So this should be this, A, B, C, then we have E, A, B, C, A, B, C, and see that, here we have 4, 4 is B, and here we have 3, 3 is C, and here we have 1, 1 is E, right? So we see B, C, E, A. So this way, if we C, E, A, B. So, with the identification of these guys, we get exactly the same multiplication table as the previous group. So if I make a map, from say, a map from say Z4 to the multiplicative group modulo 5, where what we do is that we say, the map is such that one from the 0 from the first group, sorry, that should be 0. 0 from the first group goes to 1, and then 1 from the first group goes to, say, 2, and then 2 from the first group goes to, say, 4, and 3 from the first group goes to 3. Then we see that, and that the first group has the plus mod 4, and the second group has multiplication mod 4. These are the this is the map between the two different group structures. So then we see that we have an isomorphism, right? So this is an example of an isomorphism between two groups. Okay, is that clear?
Yes, sir.
So what we have here is a one-to-one correspondence. It's also onto, and that's not enough. The fact that the two group multiplication tables match up mean that the group structure is also preserved. Okay, that's the important thing. Okay, let me just make a couple of comments. So this is kind of a trivial example, but I think it's instructive. Is that even here, we had to think a little bit. In a group, map is one-to-one and onto. Number 2 is that in a group structure is preserved. So that means it's, number 3, this means, this is a group isomorphism. Okay, any questions?